Okay. Yeah. Yeah. Good morning, all, and thank you for taking time to join this webinar on a Sunday morning. Today, the topic of webinar is YOLO V7, the latest and the most powerful object detection algorithm in the YOLO series. So today we will try to understand what are the new improvements introduced into this YOLO V7, and we will also do a hands-on training um, on a custom data set. So let's get started. This is the outline of today's presentation. So we'll start with a quick overview of YOLO series, and then we will dive into the details of YOLO V7 paper. We will cover two main topics. What are the architecture reforms that has been introduced to make this YOLO accurate and faster, and also like what kind of pragmatic model optimization techniques has been used by the authors to improve the model performance. Finally, we will end the session by having a coding hands-on on training YOLO V7 on a custom dataset, closing with the summary. So YOLO series or a family of one-shot object detectors, and they are also very important because they are real-time object detectors. So it was first introduced in the year 2015 by the AI scientist Joseph Redman when he was working in University of Washington under the supervision of Professor Ali Farghati. Um, until YOLO was introduced, it was mainly focused on OCNN-based architectures, which actually is quite accurate compared to the previous models. But the main limitations of such models is the inference speed. It was taking initially before OCNN came. It it took 20 seconds to actually process an image, and then after improvements from RCNN, they moved to fast RCNN, and from fast they moved to faster RCNN. But till with even with all these improvements, it took 2 seconds to process an image. And as you know that our modern video grabbing devices, they work on 30 frames per second, which is basically like it takes 22 milliseconds per image. And since this takes 2 seconds, it has a lot of lags. I mean, it is doesn't have some practical importance to apply on real world object detections. So then Joseph Redman came up with this concept of you only look at once, where you don't do like object detections on two stages. First, you get the region proposals and then apply the uh, object detection on these region proposals. So he came up with a framework which takes which does all at once. So that is the main significance of YOLO series of object detectors. And since then, there were a lot of improvements were made, uh, eventually creating new versions of YOLO. So in 2015, as I mentioned, it was YOLO version 1. And then the same author, Joseph and Ali, they improved this method and they released the YOLO version 2, which was better performance and faster inference and even more stronger because they could now actually infer on 9,000 different types of objects. And then in following years, they made some incremental improvement in improving the accuracy and inference speed. Um, then what happened was some interesting thing happened where Joseph left the AI industries. He stopped working in computer vision and AI. And then there was another person, Alexei, who actually took over the GitHub of from Joseph, and he ported it to PyTorch. Basically, Joseph developed a framework called Darknet, and that was written purely on C. And they actually then other developers adapted this Darknet framework and they moved it to Python and PyTorch. And that is where this YOLO v4 came with, along with a lot of other modifications to the architectures and model optimization. And this actually is a very it's like widely used YOLO's model. And in the same year, quite a couple of months later, there was another model released, YOLO v5. It was the first YOLO model which came without any paper. Just they released a GitHub. It was developed by a company called Ultralytics, and the main USP of this is like they are very developer friendly, and it gained a lot of attention, and a lot of developers started using this report to develop their own custom object detection. And in the same author who actually developed YOLO v4, they worked or they collaborated to came up with the improved version called scaled YOLO v4, and that is basically the history till 2022. So recently, a couple of months back, there was a new model released, YOLO v6. It was not from the YOLO v4 authors, but it's basically from a company called Meituan, basically a Chinese e-commerce company. They released this, and immediately after releasing YOLO v6, the authors of YOLO v4 they came up again together, and they released YOLO v7. And you're looking at the results of YOLO v7. It immediately gained attentions from all over the world, and everyone started talking about it. And I was also motivated to actually read about it, and that is the reason today we are actually presenting this webinar. Uh,
Before there are some questions, I believe, on the chat.
okay, just 1 second. Uh, can you please go full screen? Where does YOLO X comes in this timeline? Is it better than any of these YOLO models? Okay, there are many other YOLO variants like YOLO R, YOLO X, PP YOLO. I think one of them will be YOLO X. Uh, I have not done a one-on-one comparison with a YOLO X with other YOLO variants. So only after looking into their results and then benchmarking it on to your custom data sets, then only we can tell. Yeah. I think if you press on 3 buttons, it gives you option to go see full screen. Okay. Why YOLO v5 is still popular in the industry despite other models? Okay. So I think the main reason is the how the code is being implemented. Like it is very developer friendly, and they maintain the code repo very well, and they have good documentation, and it is they could you can easily understand how you can reuse the code for your custom data set, and that is the main reason actually. Yeah, right. So let me continue here. Okay, so now at a high level, right, this entire YOLO series of model, they follow a basic common framework. Like, and this framework has three main components. Uh, One is the backbone, neck, and head. The purpose of that backbone is basically the main computational block of this YOLO framework, and its main purpose is to actually extract the feature maps from the input image. And these backbones are mainly convolutional neural network blocks. For example, it could be a ResNet, or it could be a darknet, or it could be CenterNet, or like those convolutional neural network based backbones. Basically, you pass an input image and it gives you a set of feature maps. Now, between the backbone and the head, there is an intermediate neck component is there. And the main purpose of this neck is basically fusing the different feature maps that comes out of this backbone. So essentially, they collect feature maps that is coming out of these backbones, and then they efficiently combine and fuse this, and then they create a feature pyramid. So for example, one of the problems in object detection is how can you handle objects at different scale, right? So the same object, when you actually zoom in, it looks bigger, and then when you zoom out, if you look at a very long distance, it looks smaller. So these kind of problems can be handled by creating feature maps at different scales, and then combining all these feature maps at different scales into one single feature pyramid. And finally, the head. The head is basically a multi-head output layer. It has a multi-task outputs. So one of the head will actually outputs whether there is an object is present or not. Basically, that is the objectness of your model. Another will detect what class this object belongs to, whether it's a cat or a dog or a car, like that. And then another head will determine the bounding box coordinates, the x, y, w, h of your objects, the relative location of these objects in the image. Now you can, this is a small, comparison table of what different backbones, neck, head has been used in YOLO V3, V4, and V5. And so this is in all of these, it's fully convolutional neural network based. And later on, and there were also models that were based on transformers. But all these YOLO series are based on convolutional neural network based backbones. So for example, YOLO V3 used a darknet, and then V4 they improved this darknet, and they came up with this cross stage partitioning, or I'm not sure what is the P means, cross stage PNet, and then they combine with this darknet. And then it is also the same thing used in YOLO V5. And for neck, I said it's like fusing the future maps coming out of backbone. So you could use either a FPN, Future Pyramid Network, or Spatial Pyramid Pooling, or Path Aggregation Network, like that. So finally, in head, it's basically, as I said, it basically gives you a bounding box into 5 plus C output layer, which basically the 5 is 4 bounding box coordinates plus one for the class that the object belongs to. And the laws, you could either use binary cross entropy most of the time, and then logic loss functions. For the bounding box, they use regression laws like L2 laws or L1 laws, whichever you want to use. So that is a high level overview of YOLO framework. And now what a novelty this YOLO V7 introduced, which made this architecture more accurate and also faster. It can be categorized into two things. One is the architectural reforms, um, and another is basically the optimization techniques. We will see it in the next slides. In architecture reforms, they mainly did two things. One is extended ELAN, another is the model scaling for concatenation based models. Um, mainly what is this extended efficient layer aggregate network is um, like in simple terms, it they created an efficient backbone that leads to efficient model training, and which eventually leads to more better model accuracy. Uh, so the following factors were considered when they redesigned this backbone architecture. So how the memory access, the what is the memory access cost of storing all these layers and model parameters? How is the input channel ratio, or like how many number of channels is there in your input layer, and how after passing through a certain convolutional block, how the output channel is increased or decreased, this input output channel ratio. Now what is the amount of element wise operations that is going on this convolutional computational blocks, and how efficiently the gradients are calculated and then they are back propagated from the from the output layer to the layers in the models, so that the weights are updated efficiently, which leads to faster convergence of the model and improvement in the accuracy. So initially, they used other backbones such as ResNet and let's say EfficientNet. Then, as I said, they eventually started using concatenation-based models like a DenseNet. The main purpose of DenseNet is actually overcoming the problem of vanishing gradient, where when you make the model more deeper and deeper, the back propagation and the gradient path is getting a stable training of the model becomes very challenging. So because of that, what they did is um, they aggregated and they passed um, the model output feature maps to the every other layers, and because of this there was a lot of redundancies at every layer, because the output of every layer is passed into the next layer. So then they came up with this VOV net, where they don't want to do aggregation for every layer, but rather they say that it will all done at once. So it is like one shot aggregation. So they came up with the concept of one shot aggregation. So then they improved this method by introducing cross stage thing, and then it was then further improved, and then they came up with this efficient layer aggregation network. So all in all, what they are trying to do is how to efficiently train your model with less computational cost and a better convergence and improving your model accuracy. And with the YOLO V7, what they did is they took ELAN, and they what they did was they introduced three types of things. One is the expand cardinality, and they used shuffle cardinality and the merge cardinality, which means like they expanded or they make the model wider, and they after what they did is they shuffle the layers, and then finally after shuffling all the layers they merged it, and that is how I mean cardinality means improving the number of parameters actually, but you have to improve the number of parameters in such a way that it doesn't you don't do a redundant parameters are there, which is does not helps in any of your model training. So that is extended ELAN. Another is what they introduced is the model scaling. Now, what is the purpose of model scaling? Uh, so we know that we deploy the object detection model into different types of devices. So some may deploy it into GPUs if they can afford it. Some they may have like a very basic GPUs. Some of the requirement is they have to deploy it into mobile devices or edge devices. So accordingly, the model has to be scaled up and scaled down. There is always a trade-off between accuracy and the inference speed. You can note that even in YOLO v5 or YOLO v5, they always have different variants of these models, starting from YOLO v5, large, medium, yes, small. They even go further and they call it as nano. So all these are scaling down and scaling up to meet your accuracy and speed requirements. Now, how to do this model scaling more efficiently? And that is where the concept of compound model scaling comes. Typically, what you can do is if you want to search, if you want to do a model scaling, you actually take into account four things, right? One is the depth of your model, width of your model, your resolution, the input image resolution, and probably various other things. So these are the main factors that you have to take. So now how to, which one to get, whether you want to make the model more deeper or you want to increase the width. So we don't know that. We have to try and find it out ourselves. So that is why they normally do neural architecture search, where it sweeps all these dimensions, the width, and the height, and the resolution, the depth, and it finds the optimum values for these three attributes. But doing a neural architecture search is very computationally intensive, and that is why in efficient net they can come up with the concept of compound model scaling. If you want to understand compound model scaling, we have done a session on efficient net earlier, so we can talk. But for today, we will actually not go into that method detail, but we will just highlight how this compound model scaling was adapted and modified for YOLO v7. Okay, so this compound model scaling, what was developed in efficient net, is not specifically for concatenation based model. But in YOLO v7, they are using concatenation based model, that is like, take for example, darknet, where at every layer they concatenated the previous layer's outputs, right? And because of this concatenation, this width and depth are all interrelated. If you change depth, if you actually change the depth, the width of the transition layer will get changed. So because of that, they came up with a new way of computing or calculating this model scaling, where this width and depth are all interrelated, and they are actually scaled in coherence with your needs, like whether you want a bigger model or a smaller model. Okay, this is the main concept. And finally, so as I mentioned that there are two topics that was introduced. One is the architecture reforms. One we saw, it was extended ELAN. Another one was model scaling, right? Now they also in the paper they explained what are the different model optimization techniques they used to improve the model accuracy and inference speed. One is model reparameterization method. Another one we will see is where the label assigner, or the course for auxiliary and find for lead loss. This what is model reparameterization? Um, it is more similar to model ensemble. So model reparameterization can be done in two ways. One, you can do it at a model level. Another is at a module level. So say at how they do it at model level is, say for example, you have a model, and what you do is you train the same model in a different training data. So it is the same identical model, but it is trained on a different training data, and you get two or three models: model one, model two, and model three. And then what you do is you actually take a weighted average of this model to get your final model. So this is one type of model level reparameterization. Another type of model level reparameterization, what you could do is you could take the model at, let's say, iteration 100, and then you could take another model at iteration 200 and another model at iteration 300, and then you could basically take a weighted average of all these models and use that as your final model. So this is actually a model level reparameterization. Now, there is another one more type of reparameterization, that is the module level reparameterization. So what this does is it splits the model into multiple modules during training. This is basically during training, they split the modules into multiple modules, and then during inference, they combine this multiple modules into one single equivalent module during the inference. So to put it into simple terms, this model reparameterization, either as a model level or a module level, is basically equivalent to model ensembling. So we know that model and ensembling actually helps to improve the model accuracy, which is basically the wisdom of crowds. Like instead of depending on one single model, we train like multiple models. We get the output of these multiple models and take average, or aggregate it. Either it could be average or maximum, or any types of aggregation. This is the same thing that they are doing it in this YOLO V7. So in module level, basically they were doing module level reparameterization, and how they did this, it is also very experimental and very pragmatic. So they tried with different combinations. So in a plain vanilla network, there is only convolution blocks, and there is no skip connection, or that what you see it in ResNet. Now, there was also a paper called RepCon, where this kind of blocks, right? This is basically coming from a VGG paper, right? This this is basically coming from this VGG paper. Now, what they did is they took this VGG blocks and they added residual connections, and they made it as RepCon. Now they took this Regcon and then the plain net, and then then this is ResNet basically. So you have this connect when you have a skip connection, then it becomes a ResNet. So then they have a Repcon with the residual connections, and then they combine Repcon with con and with residual connections, and then they interchange the order. They put con first and Repcon following that. So all these, combinations of, including residual connections, using either the con block or repcon block and putting it first or putting it second. They tried all these combinations, and then what they found was that whatever they found working was put into tick. So these were actually working, these four things, and these things were actually not working. So wherever they were, it was giving poor performance. So this is actually poor, very experimental, and they found which module level reparameterization worked and which didn't work, and then they used it.
So there
Right.
are some questions, Bismillah, on chat.
Okay. Okay. Why YOLO is using binary cross entropy instead of categorical cross entropy as it is multiple class? Yeah, actually, it is not entirely true that it is using binary cross entropy. So it's basically a multitask class. So it has three tasks. One is to identify whether object is present or not, which is basically a binary classification, and that is why it was mentioned in the table as binary cross entropy. But there is two other laws is also used. One is a regression laws, which is basically either it could be L1 laws or an L2 laws. And the third loss is basically what you mentioned. This is categorical cross entropy, where it makes a multi-class classification, whether the object belongs to one of the 80 COCO classes. Okay, so probably that slide was not 100% correct. So it is not either binary or it is not either categorical. It's basically a multitask class. Okay. I hope that is clear. And there's another question. Does module level split mean that we are having specialized models for different classes or cluster of classes? If not, what is the difference between module level and model level? Yeah, yeah. I think I explained this. No, I think it is not that we have different models for different classes or different group of classes. No, it's not like that. um, uh, it's basically that you do reparameterization either at a model level or you do it at a module level. So in model level it is very straightforward, and that is where mostly it is used. Like you actually train different models with different training data. Okay, and then you actually combine these different models into one final model after aggregating the weights of these different models. And another way of doing model level aggregation or reparameterization is like you have only one training data, and what you do is you do like you do checkpoints, right? Like let's say you have 100 epochs or 1000 epochs, let's say, and every 100 epochs you save a model, and that becomes like a different versions of your models. And finally, it's not that you use the model with only the best metrics. You take models from different checkpoints and then average them, or give weighted average them and then get a final model. Okay, it's a similar to model on sampling actually. And this is model level, and module level, as I explained, they actually split this modules, one module into multiple modules during training. And then in inference they combine all this. They actually like if we have like 4 different modules, they actually take again an aggregation. It could be like a weighted average or average, like that, and they make it into one single module. Okay, what it means is that different modules learns different things. Okay, and so it gives a more robustness. So one will learn a more one module will be more accurate on a one class, another module could be more accurate on another class, or one module learns different attributes of the image, another module learns another attribute. So now during inference you can actually combine and take a weighted average of them. Okay, I hope I have explained it. Yeah, you can read the paper in detail and you can know what is a retcon. So retcon was again another paper which basically is taking the VGG blocks and adding like residual connection to that. Okay, so let me proceed, and then we'll come back to this. We'll look into the papers if if we have time. So the final technique they used to in this paper is they call it as label assignment. You know how efficiently you can do label assignment in your head of your model. So normally what you see is, let me just see if okay, this is better. So normal model, what it has is it has a set of layers, and then finally you have this detections, right? So this the loss is actually calculated from this final detection layer. Now, what you can also do is that instead of calculating loss, only at the final extreme layer, you can also create auxiliary heads by getting the output from the intermediate layers and then calculating auxiliary loss from these auxiliary heads. So you feed in your ground truth to your lead head, which is basically your final detection, but you also calculate auxiliary loss from your intermediate layers. And because of this, the researchers found that your model training is more stable and the model convergence reaches at relatively faster. So this concept of using auxiliary head and calculating auxiliary loss is called as deep supervision. Okay. It's a technique of using multiple heads. The main concept is to add an auxiliary head in the middle layer with assistant loss as the guide. Now, the way you design this auxiliary loss is important. Now, what they found is instead of using hard labels that directly comes from ground truth, they create soft labels, which are basically created by combining your ground truth, which is your hard labels, and then getting outputs from your lead head, and then by combining this output of your lead head and your ground truth, you can actually create soft labels, and using those soft labels you calculate your loss. Okay. um, so uh, this is how what is label assignment is mean. So instead of using ground truth as a hard label to calculate your loss and then back propagate to update your weights of your model, you actually do a soft label assignment, and these soft labels are actually calculated by combining the outputs of your model with your ground truth. Okay. And so since we have two heads, one is the lead head and the auxiliary head, what they do is so these the label assignments are calculated independently. So the lead head is independent of the auxiliary head, and the auxiliary head is independent of lead head. Now in this YOLO V7, what they did is they did the lead head assisted uh, calculation of your auxiliary loss. So the label assignment is done from using your lead head, and this label assignment, the soft labels that is coming from your lead head is actually used as a ground truth for calculating your auxiliary loss. And these auxiliary laws are actually calculated using the outputs from your intermediate layers and not in the final layers. Okay. Now, either you could do like a course. Like just a simple combination, or what you can do is you can do a course to find combination of this lead head and auxiliary head loss. So you make a fine loss here, and then you make a coarse loss here. So the way you combine this auxiliary loss and the lead head loss. So by this way, they were actually able to improve the model performance. Okay, I'll see if any question is there. Okay, I don't see any questions.
Bismillah, if I am using this, I can use a pre-built YOLO V7 model, right? So I don't have to worry about tuning it. Or do I have to worry?
Yeah, you have to worry because these models are trained on Coco, which is basically 80 classes. And you can take this pre-trained YOLO V7 and then fine tune it for your custom classes.
So I have to worry about tuning it in that case, huh?
Do domain adaptation for your custom data set.
Because in earlier YOLO, even then it was like that only. Yeah? It didn't work off the bat for your custom images, huh?
No,
You
no,
had
no, I don't think any of the no object direction frameworks works out of the box for custom classes.
right, correct.
Yeah.
So which means I have to worry about tuning it, and I have to understand its internal mechanics here, right? So to be able to tune it well.
Ah, yes. Like, I mean, it might be that if it might work out of the box, you just have to do, just change the data set. Instead of using Coco, you just say that, this is my new data set. These are my new set of classes. And the YOLO framework is going to fine tune the model for your new set of classes and new set of data. Okay. With the default parameters, it might work and you might get a good model that can actually work on your custom data set.
Mhm.
But in many cases, it will not be the case. You have to go and fine tune it, do hyperparameter tuning, try different losses, different learning rates, all those things you have to do.
No, but then if you look at OpenAI algorithms, right? So they have done some superb work with Delhi and all, where you don't need any custom tuning. But I guess that's trained on web scraping, entire internet data. So
Yeah,
the
but
I mean, the idea is to the question main ask is how do we get to no code vision launches, or we have no way of reaching no code vision launches.
yeah, I don't think no code vision launches is only that you abstract the coding from the business users,
Hmm.
but and at the back end you actually have to do all these things and then give the result to the users. So users, different business users will come from different business. One will come from industry domain, one will come from medical domain, one will come from retail domain, and their target classes are different. Some wants to identify juice cans and biscuits, another want to identify cancer cells, another want to identify defects in the machine parts. So these are all different and they have the data set and then they have the labels, but they don't know how to train. If they just upload the data set, at the back end, we actually have to do all this fine tuning it and give them the result to them, right?
Right. So okay, fair enough.
Hello.
Hello? Yes.
So that we can use YOLO V7 for multiple domains, so for medical domain, medical domain, all domain we can use for
Yes,
common data.
yes. So it's basically like a domain, agnostic, but it will not work out of the box. This YOLO V7 is now trained on Coco dataset, which has like 80 classes, right? Now you cannot expect this model to work on detecting cancer cells for your
Yes,
medical.
actually, the medical domain it cannot be used.
Yeah, it cannot use, but it can made to be used. You understand?
Yes, yes.
Okay.
So compared to 3, 4, 5, 6, 7, so 7 is the latest. YOLO.
Yes, correct.
What's the accuracy level?
So accuracy is at 60 MAP, and it can actually do from up to 150 FPS. Okay. So yeah, so this is the experimental result of YOLO V7. So as I mentioned, they are like different variants starting from a tiny model up to a large model. So their mean average precision is around 60, like 56, and they can also reach up to like 160 to 286 FPS, using a tiny model. So this tiny model is mainly is focused on edge devices. Okay, if you have an edge device, then go for this. Okay, and then if you have a normal GPU, then probably you can actually go for this. So if you have a very good GPU just deployed in cloud, then you can actually go for the most accurate model. So if we do a comparison with other YOLO models like YOLO R, YOLO V5, YOLO X, I think someone mentioned that YOLO X. So PP YOLO, scaled YOLO V4. Okay, so YOLO V7 is somewhere, it's here. So it is almost significantly better than all other models in terms of accuracy. So this is basically the accuracy, and this is basically your inference speed.
So
So
what about comparison with vision transformer or DET or detection transformer?
okay, yeah. So DIT was it's not purely 100% transformer. It's both convolution plus transformers. So then we have this vision transformers, and using vision transformers, they came other object detection models, right? So the latest one was the Swin transformer. Okay, so it was basically was the state of the art on the COCO benchmark, and YOLO V7 also outperformed this. So maybe we can quickly look into the benchmark result, which will give you a better idea. So if I actually, okay, so here is the COCO benchmark data, this one. So now you can see YOLO V7 is outperforming every other model. Now if you go down, so there are two types of models are there. One is convolutional neural network based models, which majorly comes into YOLO framework. Another is based on transformers, right? So these are, as you mentioned, these are based on vision transformers. So this is basically the Swin transformer. So it was actually it was highly performing, maybe like 1 or 2 months back. Now you can see that YOLO has outperformed all other previous SOTA models.
So the leaderboard changes almost every week or every month. So
Yeah.
okay.
So yeah, correct. So as you can see, every year or every month, the leaderboard changes. Yeah. So here is our data. I think it was in 2020 it was released. Okay, so that is experiment and results of YOLO V7. And yeah, that comes to the conclusion of this webinar. So in summary, what we studied is we got a general overview of YOLO architectures starting from 2015 when it was first introduced by Joseph Redman, what problems they solved in hand, and then how the YOLO architectures evolved through the years, and now in latest we have YOLO V7. And what we also under
Bismillah, you still have a hands-on workshop, right? So
yes,
because
correct,
it's not end of the session yet.
yes, correct. So we understood now what are the different aspects of this YOLO V7 that is explained in the paper. What architectural reformers was introduced, what are the different optimization techniques was introduced in this paper, and we did a quick comparison of YOLO V7 performance with this previous uh, alternatives. So now we'll get into the hands-on coding.
There are a few questions remaining on chat.
Okay. Does YOLO V7 architecture helps in tackling detecting occluded objects? Okay, so there is no any specific on this topic of solving occluded object detection problem. It was mainly focusing on improving the COCO benchmark metrics and also the inference speed. And does final loss comprise of auxiliary loss as well? Yes, correct. So that is how the model weights are updated. So in a typical normal way of updating your weights, you only calculate weights at your detection head. It's the very final layer. But in the concept of deep supervision, you not only calculate loss from your lead head, you also calculate loss from your auxiliary head, and you combine these two, you back propagate these losses to update your weights. Any suggestions on best object tracking method? You could use deep shot. Uh, yeah, probably there are other methods, but the one that I know and I have used is a deep shot, and it works pretty well. Comparing transformers to YOLO V7, which is lighter model. Okay, yeah. So definitely YOLO V7 will be lighter compared to transformers. Um, so that is why the main importance and significance of YOLO framework is they are all real-time object detectors. So they can achieve the FPS what this real-world industrial applications will demand for. So you would actually need at least minimum like 20 FPS like that. So it should be like around, and also like the hardware configurations of your industrial devices is they will not have GPUs, they will have only basic CPUs. So how can you do real-time inference on such limited hardwares? And that is why these YOLO models are very popular. So I don't think transformers can actually help there. Yeah. Okay. So now let's move into coding. So
You can share this link on the chat.
okay, sure. Okay.
Did you get a chance to try it on CellStrat Hub?
Yeah, I have it. But we will do only inference on CellStrat Hub.
Okay.
Okay. So first I will start with inference on CellStrat Hub, and then we'll move on to training. You can also do training on CellStrat Hub if you have GPU instances, which is available at higher tiers, right?
Yes.
Yes.
Correct. Correct.
Yeah. So in free tier, you only have CPUs. So because of that, we will do only inference today. But it is also possible to do training on CellStrat Hub if you have subscribed to higher tiers and you have GPUs where it has GPUs. So I think Gamma tier has GPU, I think, right?
Correct.
Yes. So since you see this Gamma tier has 16 GB NVIDIA T4 GPU, you can do the training here. But in the lower tier, since it has only CPU, um, you can do only inference there.
So Jack Martin, actually, yeah, free tier only has CPU. So you can reach out to us if you want to upgrade to the premium tier after this webinar.
Yes. So this is basically CellStrat Hub, and as Vivek has explained, so this gives you a platform to do all your machine learning development, deep learning development into it. It has a lot of other key features like API marketplace and easy deployment of your models. It does a lot of heavy lifting for developers, so you can focus on learning deep learning and deploying these models instead of being challenged by the technical stuffs in deploying these models. Mm. Okay, so normally what you do is you can actually register in CellStrat Hub, and then you can create an account, and then you can start a workspace. So it will create a Jupyter Lab environment for you with pre-installed deep learning frameworks like PyTorch and TensorFlow, and it is ready to use mm, straight out of this workspace. So you don't have to go and install PyTorch and TensorFlow again. It comes pre-installed for you. So now I logged into my CellStrat Hub. I started my workspace. So in a minute, it launches the Jupyter Lab environment. And when I click this button, it creates my Jupyter Lab environment. So this is basically my development environment where it has the Jupyter Labs and other PyTorch and TensorFlow. And here I have created a Jupyter Lab notebook, which basically comes from the YOLO V7 GitHub itself.
Could you download this, right click download and send it to us via Google Drive or something? Or you have it in Drive, you can just share that link.
Yeah, sure. So this
is different notebook than Colab one you were showing, right?
yeah. So this basically comes from here only. So I can share this also. I'm just showing you like you can directly the development environment, or the environment is ready to use. You can just run the Jupyter notebook directly from CellStrat Hub.
Which is the file in that GitHub test dot?
Okay, so in that one, this is the file.
Open in Colab. How did you reach?
I mean, this if you click this button, it will open in Colab.
Okay, and then I can download it, right?
I downloaded it and then I imported it into CellStrat Hub.
Right.
Okay, and then I ran it within CellStrat Hub.
And this file is different than the one you shared from the PPT.
Yes, correct. Yes. That is training, but it has only inference because since I'm using free tier, I have only access to CPU, where I can do only inference. Okay. So within this notebook, basically installing YOLO V7 by cloning the YOLO V7 GitHub repo. and then doing a pip install of the requirements. Once the YOLO v7 is installed, I can then get the pre-trained YOLO v7 weights. Okay. And with this YOLO v7, I can do inference on this images, which basically is calling this detect.py from this YOLO v7 folder, right? So what are the parameters you have to pass? You have to pass in your model weights, which we downloaded in the previous step. And then you have to give a confidence value for your model predictions. In this case, it is 25. What image size you have to use, and where is this image, where is your input image. So I'm doing a single image inference here. So this detect.py is run, and then your model outputs are stored in this folder, runs folder. Okay, as it will create a folder, and then it is stored here, which you can also visualize within your Jupyter notebook. Okay, so this is how you can do YOLO v7 inference within CellStrat Hub. Okay, it has 4 major steps: cloning and installation, and then running the detect.py, and finally visualizing your results. I think it's pretty straightforward here. So as you can see, it's very user friendly. This environment, you don't have to install the PyTorch or set up your Jupyter environment. So that is one thing. But if in case if you have upgraded tier where you have GPUs, you can also do training here. Okay, but I'll just show you how to do training in Colab. But it is also possible that you can do the training within CellStrat. Okay. So now I will move into the training part on custom dataset. So basically I got this notebook from RoboFlow. Yeah. So thanks to RoboFlow for creating this notebook. So what I did is I just essentially used that notebook. I just mounted my drives, and I installed the same thing. I cloned YOLO v7 and did the installation, and then I imported a dataset called swimmer dataset, which again is basically coming from RoboFlow. These are annotated dataset of swimmers. I downloaded it, and then I got the weights, pre-trained weights. But now instead of using detect.py, I use train.py, and then I say that my data set is located in this location. These are my initial weights to be used, and I have to train it on GPU. Then I have to mention it as 0, and what is the configuration file I'm using it, how many epochs I want to train. So if I run this after the 55 epochs, this is my mean average precision for 50% IOU threshold, and this is my mean average precision for an interpolated between 0.5 to 0.9 Y threshold. If you want to get a detailed insight into your results, then you can actually go into your runs folder, right? It creates a folder called runs. Within that runs, it has a train, and it creates folders for different experiments you run. And within that, it has a lot of output files. So one of the file would be like like the F1 score. So since I have like only single class, it is created like one F1 score, and this is in the x-axis. It has the confidence, which basically is your model confidence, and the y-axis is your F1 score. So your F1 score is high at a confidence of 0.4, and at I think 0.27 it is 0.94 F1 score.
Can you share
Likewise,
the runs folder from your Google Drive so we all have that data as well?
do you want this data?
Yeah, the entire runs folder is needed here, right?
Yeah. So if you run it, if you're able to run this collab, it will create this folder for you.
Oh, is
But
it okay?
I can also share it. But
We don't have to have it from before.
no. It will create for you. Don't like. I mean, I have given this collab for everyone. Okay.
Hmm.
And what they have to do is they have to run cell by cell, mount the drive, and then wherever you have this. Wherever you want to save your results, just change your directory to that. So here I have a directory called YOLO v7, right? Within that, I am running this collab notebook, and and then cloning my YOLO v7 report to that, and then installing all those script installed. And then this is something that you have to do it. You have to create a RoboFlow account and create an API key and use that API key to download this data set. Okay. If you're not, if you don't want to go to all these things, probably I will give you this data set because I already downloaded it, right? Um, so what I can do is I can just upload this data set.
Yeah, that will be easier because each person trying to get that RoboFlow license is
Yeah,
challenging.
correct. So you can share it. So I'm sharing this GitHub of my swimmer dataset. Okay, you can download this swimmer dataset and then put it into this YOLO v7, unzip it and put it, and then give this path to this here. See, here I know that I'm using RoboFlow API, so it creates a dataset object and gets the path to here. So here it might throw error because you're not using that. So what you have to do here is you have to give the path of this folder here. You're getting it? Or
I
I'll
have to
do
keep it as a zip file or I have to unzip it in that folder?
unzip it. Yeah.
Okay.
Or I will do one thing. Yeah, I will also run it since we have some time.
Your mounting folder has to be changed as from your notebook.
Yes, correct. So I'm trying to do from yeah. So after you give permission, your Google Drive is mounted, right? So if you're actually using Collab for very first time, if you're not aware of how to mount your drive, this is how you do. You run the skill, and then it will, after you authorize, it will mount your drive. So now what will happen is now your drive is mounted. Okay. So within that you will have all your drive folders. So, right. I have a folder called YOLO v7, and that is where I'm changing my directory. So I'm changing my directory to this YOLO v7. Okay. I know for many folks this might looks already familiar, but for who are very new, I'm just explaining them. So then I cloned this into this, and then I did a pip install here. Okay. And then I could also do a then I yeah. So let's say we don't want to go through this RoboFlow thing, right? And we actually, this is also done. So but anyway, I'm just doing it again. So it's basically like YOLO v7 pre-trained weights are downloaded into your this folder, right? If you look into it, this is there, YOLO v7.pt. And then what I do is, if you run this, this will throw error, right? If you run this without changing, okay, as you can see that the dataset.location is not there because I have skipped this step. Now let's say I want to change it. It means that you basically have to get the path of this, right? And then actually change this here like this. Okay. If you open this, there is a data.yaml file is here. Okay. Now this will not throw error. So remaining things, everything is fine. Now if you run it, but you have to ensure that you unzipped this. Don't give the path of the zip file, right? Okay. So now it started trading, right? Okay. So this is a new experiment I'm running. So if you go into the runs folder and into the train folder, you can see that a new folder is created for me, experiment 3. And within this, all files will be created. Okay. Yeah. So this is going to take some minutes. So it's all fine. Like, do you need? I hope everything is straightforward. But for some folks are not familiar to how to set this up, this might be useful, I guess. Okay, meanwhile, I just opened the floor for discussions and questions. Okay, so see, in a way, this topic of YOLO V7 is not so cool or not so fancy as DALI or AlphaGo or other things. The main motivation for me to take this topic is very because this YOLO V7 is very practically relevant. Most of your work that you will do as a data scientist will be around this and not DALI or AlphaGo. So, I mean, you should know how this model is working, what are the different knobs that you have for this model, how you to actually get the best accuracy for your custom data set using these YOLO frameworks. This is where, most of the practical work will be. Okay. So I just given a high level overview of YOLO V7. There's a lot of things that you have to actually understand and get hands-on. Get deep dive into this GitHub repo and go into each and every file and see. Okay, especially these config files, right? Okay. What does this config file mean? Like, what is this? What is this depth multiple means? What is the significance? What does this anchor? Why they are using these values? Why can't they use 100 comma 200 instead of these values? what backbone they are using, what is this configuration means, right? All these things will be, very, very crucial to actually fine tune it to a custom data set. So yeah, I'm just open for questions and discussions. If you have anything to share from your experience on getting the best out of this YOLO for no real world applications, please feel free to share. Yeah.
Just check if you answered the questions.
Yeah, sure. So is it possible to share this GitHub repo with specific resources we used in this demo? Yeah, so there is only one collab notebook that I have shared. That is all the required information, to get you started. What does data YAML file contains? If we want to train on our own data, which annotation tool we use and which format we export labels. So the data.yaml file contains the information about your training and validation data. So it will tell you where is your training data located, where is your validation data located. If I can open that. Yeah. So if you actually go into your swimmer and data.yaml, it just tells you what are the different classes your model is going to train on. I have only one class, swimmer. What is the number of classes? One. Let's say if you have like 20 classes, all the names has to be written here. How to say dog, cat, all those things. So now you have to say I have three class and these are the three names of those classes. You have to tell where is your training data located, where is your validation data located. That's all. So it's basically your data configuration. Okay. And in answering your question about annotations, so you can use either open source tools like CVAT or Label Studio and export them into YOLO format. So there are different types of format like Pascal VOC format, Cocoa format, right? Like that. They also, these YOLO frameworks, they have their own format. It's basically, it's like they have images and then they have a text file for each and every image. And this text file will contain bounding box coordinates. That's all. That is the YOLO format. Nothing rocket science here. So you can export it as a YOLO format. Mm, yeah, I think pretty much all question is answered. And I hope you got a good, intro to what this YOLO V7 is about. And I recommend you to actually read the paper. So this is the YOLO V7 paper, and I have read it myself in detail. And so the main topics are model reparameterization, model scaling, and how they use extended efficient layer aggregation network. Okay, if you want to understand in detail what is this extended efficient layer aggregation network, then you have to understand this paragraph. Then how they do model scaling, module level reparameterization, how they do this label soft label assignment, and how they combine lead head loss and auxiliary head loss, and how they made the lead head to actually guide the auxiliary head loss. Okay, all these things are explained here. Okay, apart from this, there are other topics also they have used to improve the YOLO V7 model. So one is they used a batch normalization. Um, in the batch normalization, they actually made the combined it with convolutional. Um, there is like a convolution layer, then batch normalization, then the noctivation. So this topology, right? This is what they used. Okay, and then there is something called EMA, which basically is like It's mainly for the inference. This is again another type of uh, improving your inference accuracy. Okay. And one more important thing I think I missed is that this YOLO V7, they are in comparison to the previous models. This YOLO V7 is purely trained on COCO dataset, and they did not use any pre-trained models that was trained on ImageNet or any other dataset. Okay, so in YOLO V4, those backbones, right, that darknet and CSP darknet, they were actually pre-trained on ImageNet, and this backbone actually extract feature maps using this pre-trained, and then they do this feature pyramids and then detections. But in this YOLO V7, they did not use any ImageNet. They only used COCO dataset, and it was trained from scratch. Yeah. So this is the paper, and there are many other papers that you want to refer to. Like if you want to know about CSPNet, someone asks what is repcon. It's basically taking the VGG and then improvising on it, and then yeah, this is basically the VOVnet. So this is what I was telling. Instead of doing layer-wise aggregation, right? So this basically is this concatenation, this symbol. So earlier in DenseNet, they were actually doing concatenation, as you can see along the channel for every layer, and because of that, it becomes very computationally intensive. So rather they said, okay, we will do only one time aggregation at the end. Okay, yeah, I think this is pretty much how much data needs to be labeled for fine-tuning YOLO V7 model. I'm working on car and truck. Okay, so car and truck is very easy. So it will work, let's say 100 images per class. It will work straight out of it.
No, binary classifier can be done with basic CNN, right? Car versus truck.
Now you want to detect the car and truck,
Yeah, I mean that's
like vehicle detection.
yeah. I mean if it is not bounding box, if it is just image classification, basic CNN will give pretty good accuracy given a large data set, right?
Yes. So
Like in our
yeah,
deep learning pack, we have house versus boat classifier. It gives pretty good accuracy. Basic CNN.
yeah, correct. So he has to clarify whether it is a classification or an object detection.
Yeah, bounding box and all it is complicated. Then you have to bring in one of these or faster or CNN.
Okay. Also, is there a place or a hub where we can find the fine-tuned models? Yeah, I'm not aware of one such hub. You can actually try Hugging Face, and I think pretty soon even CellStrat Hub will have a lot of models, right, Vivek?
Yeah, we are continuing to grow our project marketplace.
Yes.
Currently, a lot of our models are based on COCO only, whether it is DETR or Vision Transformer or YOLO V5 is also there. But vehicle detection specifically, I don't recall any of our packs has because it's a narrower use case. But we have a lot of projects on CellStrat which can be used for jumpstart training for custom data sets like vehicles.
Yes. So we have this marketplace, even like I think the community can actually deploy their models here, right?
Yes.
So
So
we
we
have
have
different types of models, object detector, But this is like a general purpose object detector.
Coco. This one is
Yes.
Coco only.
Yes.
So most of the vision models are based on Coco only. So they do need a custom model enhancement for custom data sets. So over time, we'll keep growing the APIs and projects available here to cover more and more specific use cases in transportation or retail or healthcare and so on.
Yes. So this also.
On GitHub, we'll find millions of projects for almost everything imaginable, right? And
Yeah.
but yeah, setting them up is normally challenging. That's why we are creating a jumpstart platform on CellStrat Hub where things can be done more easily.
Yeah. So this is CellStrat model is already detecting all horses.
Because this may be a Coco image, right?
Yes, this is a Coco image.
Yeah.
So yeah, this is the main USP of this platform, right? It works straight out of your web browser, right? You don't have to do all these Jupyter notebook setups, collab setups, everything. So it will work.
Right. So we invite all of you to join the CellStrat internship programs or courses, and you will also then help us contribute or develop or launch APIs and projects on our platform. But certainly it is not as vast as GitHub or Hugging Face, but setting up those environments or code from there is quite a Herculean task. And our endeavor here is to democratize AI development and deployment or AI usage with ready-made Jumpstart API. So the endeavor is to simplify AI lifecycle here on CellStrat Hub. Everything is available in other portals like Hugging Face, GitHub, but setting them up is very difficult task as we know. So any other questions for Bismillah today? Okay, so I guess that brings us to the end of this session. Thanks, Bismillah. Excellent details and presentation. And details for CellStrat programs. I am sharing my mobile number here. I am the co-founder at CellStrat. So reach out to me, and we have a variety of courses and internships which I can present to you. So just reach out to me by call or WhatsApp, and we'll be happy to discuss a variety of programs we have. We have internships as well as courses available. Okay, so thank you all for joining, and we'll see you in our next webinar, in fact, next weekend itself. Have a very good one. Thanks a lot, Bismillah. Fantastic presentation. Have a good
Thank
one.
you, Vivek, for the opportunity, and thank you everyone for your time.